I will talk about the compression of file recipe data in data duplication systems. This is the outline of my talk. I will introduce again what file recipes are and why it's a nice idea to compress them further. I will introduce 4 different approaches that are in different points of the space where you can do file recipe compression. And I will evaluate these approaches using a trace-based simulation using different data sets. Most file-based data duplication systems have file recipes. The file recipes are the data structure that map from the logical view of the file system of files to the physical view of fingerprints, chunks, and containers. They are, for example, used during restore to recover the latest file content of a file. They are similar to data block pointers in normal file systems, but there are important differences. One is that usually the chunks in data duplication system are variable size, and this makes the management a bit more complex. But for this talk, the more important piece is that the fingerprints stored in file recipe data are usually 20 bytes or more. And this means they are much larger than the pointers in normal file systems. We have here a small example with 2 files, 1 file with 1 fingerprint, 1 file with 3 fingerprints, and we see here that the fingerprint is the largest amount of data stored there. In practice, in large backup deduplication systems, the file recipes can occupy a significant amount of disk space. One reason for this is that the chunk data, the chunk index, and the container grows with the size of the data after the deduplication happens, and this means, in general, very slowly. But file recipes are this one data structure that maintains the logical view of the file system, and this means they are growing with the capacity before the deduplication happens. And each new backup run with a high deduplication rate adds file receipts to the system that need to be stored. Here are 2 examples with a back on the envelope calculation to store 1 year of weekly full backups with something like 95% weekly redundancy. Around 6% of the overall capacity of the system needs to be is used by file recipe data. But if you have more runs and higher deduplication ratio, for example, with daily full backups and 99% daily redundancy, this can even grow to around 30% of the overall capacity. And this means that compressing file recipe data can lead to significant additional storage savings in data duplication systems. The basic idea is that we are not storing the full 20 bytes or longer full file fingerprint in the file recipes, but we assign, using different approaches, shorter code words and only store the code words in the file recipes. The requirements are that for this additional compression, we want a limited low overhead in terms of RAM usage, I/O operations, or storage. Also, it should only be a limited or no impact on the write and restore speed. This research presented here has been performed in the context of the development of the DW1 research deduplication system at our university, where we think that this approach is not only usable for this one system, there are certain assumptions built in, and this approach may not work for all approaches and systems. One is we are talking about fingerprinting-based data duplication systems. Some of the approaches assume that we have a full chunk index available, for example, on SSD storage. Some of the approaches are tailored to backup workloads because they use locality properties only found in these workloads. Last assumption is that we think that you need a way to get back from the file recipes and the code word back to the full file fingerprint. This may not be necessary for the core write path of the system, but we found that it's necessary for things like consistency checking and garbage collection. The first approach uses the observation that we have a significant skew in the distribution of chunk references. Few chunks are responsible for a surprisingly high number of references. Especially in a lot of data sets, we found that the zero chunk is very important. So zero chunk is the chunk completely filled with zero data. This zero chunk has nice properties that we can pre-calculate the fingerprint of this chunk and can use it. For example, in the DW1 deduplication system, the chunk is never stored on disk, it's never read from disk, and this fingerprint is never looked up in the chunk index. Also, we replace the 0 chunk fingerprint with a special 1-byte code word, and already this reduces the file of the file recipe data. This approach may also be used by other systems as well. The first approach assigned a very short fingerprint to one special chunk. Here we take the different approach. With the chunk index-based approach, we assign one code word to every fingerprint in the system. There are different ways to do this. We decided to base the code word on the chunk index data we store. We assume here that the chunk index is, for example, built by, implemented by a persistent hash table, and a fingerprint is hashed to a certain page on disk, and then the code word is built by the ID of the page the fingerprint is stored in, and a unique identifier within the page. This means for mid-size system, we can get around a code word of 32 or 40 bits. The third approach is called statistical dictionary approach, and here we use a statistical model of the usage of fingerprints in the system. It can be seen as a generalization of the chunk fingerprint, zero chunk suppression approach, because it assigns code words to highly used fingerprints. Here we determine the entropy of each chunk in the system. The entropy is a function of the probability that the chunk is used in the system, and this is a function of the number of references of the chunk in the system. This is easy to implement with the reference counting data deduplication system because we already have the number of references to a chunk. But this is only possible after we have a few runs in the system, because only then we can start estimating the entropy, and the entropy is then pretty stable. In this approach, we assign a smaller code word to all chunks in the system that are below a certain entropy threshold. We configured it, for example, in the evaluation that around 0.3% of the chunks receive a code word. This means that we can have code words around 24 bits in size, and for the reverse lookup, we maintain an in-memory reverse index that points from the code word to the fingerprint. This is similar to classical Huffman coding, but because we have billions and billions of chunks in a deduplication system, the optimal Huffman coding approach cannot be used here. This approach can be seen as a highly relaxed, non-optimal version of Huffman coding tailored to scale to billions of chunks. The fourth and last approach assumes a different statistical model. Here we are not looking at the probability of a chunk in isolation, but we look at the context of the chunk. Per chunk, we look and determine the most likely following fingerprint in the system. This is also called order 1 statistic in compression. And this most likely following fingerprint is selected as a prediction candidate based on the previous chunk and the context. If we find a file receipt and we see that the following fingerprint in the file recipe is the prediction fingerprint, we are not storing the file fingerprint, but we only store a short 1-byte code word. This assumes that the order of the fingerprints in the file recipes are likely to be similar, likely to be the same as previous backup runs. And this is the locality property of backup workloads. But to determine the most likely following fingerprint, the full order 1 data structure we need to store is too large to handle at scale. So again, we relax an optimal approach, and we are only using an estimation of the most likely following fingerprint using a constant size of data per chunk, and we store this data in the chunk index. This prediction is relaxed, it's not exact, but it's sufficient for our purpose. We evaluated this approach using trace-based simulation of weekly full backups. There are 3 different data sets in the paper. I will only explain one data set here. This data set is called the Home1 data set. It's based on quals of home directory file server at the University of Paderborn. with weekly full backups using content-defined chunking and at kilobyte in chunk size. This is actually the same data set as used for the store paper a few years ago. And these are the compression results. We are able, with the zero chunk suppression, to eliminate 5% of the size of the file recipes. This is quite a surprising number because this is a very low overhead approach, and low and 5% of the references in the system are for this one chunk. But obviously this is not enough to solve the real problem. The nice property about the page-based approach, the chunk index page-based approach, is that that the size only depends on the size of the overall data set you store. It does not depend on certain properties of the system. With this approach and usual configuration, we are able to remove 80% of the size of the file recipes from the system. The statistical dictionary approach, using the probability of the chunks, is able to remove 9.6% of the data, and we have been quite disappointed by this. If you think about that, lone 5% can be removed by the zero chunk suppression. All this additional overhead with the in-memory chunk index, in-memory reverse index, is only adding 4.6%. But with the statistical prediction approach, we are able to remove 76% of the data of the file receipts. This means this approach with the prediction fingerprints and the order one statistic is capturing the locality properties of backup workloads, and it can use these locality properties to remove a lot of the fingerprints in the system by a small code word. It's also possible to combine these approaches and to apply them in order. Here are three examples for this that are, I think, the most interesting one. The first one is the zero chunk suppression combined with the page-based approach. And we see here something that we also see in other combinations, that when applied with other compression approaches together, the zero chunk suppression is only adding 0.1, 0.2 to the overall compression ratio. So it's 5% alone, the effects are vanishing when combined. With the statistical prediction approach and the page-based approach, we are able to remove more than 90% of the overall size of the file recipes. And this is actually a pretty nice combination because we have this overhead to store these predictions in the chunk index. But if we are using the page-based approach, we need only to store the code words we already have for full fingerprints for the prediction. And this actually reduces the overhead of this combination. If we add all four approaches together, again, only 0.1, 0.2% additional compression is added to the combination of the statistical prediction approach and the page-based approach. So for us, the combination of the page-based approach and the statistical prediction approach is a nice trade-off. Let me conclude this talk with repeating that file recipes can use a significant disk space for backup systems with a high deduplication ratio. I presented new compression approaches and a combination of them to reduce the size of the file recipe data. This compression can be seen as providing additional compression, additional storage savings in deduplication systems, in addition to the core deduplication and the compression of the container data that is common in deduplication systems. File recipes are a largely unexplored territory in data duplication research. They are not mentioned much, but we found out with this research and other research that that it's a nice data structure that can be used for improving certain aspects of data duplication systems beyond compressing them. The simulation tool, as well as the deduplication system where this research was founded on, are available as open source. And I'm open for questions now, but I also will be at the poster presentation. Thank you for attention.
Hi, Michael Condit, NetApp. This is a very interesting work. Most systems that combine compression and deduplication compress the deduplication chunks, and so they layer deduplication on top of compression. Yeah. You're layering compression on top of deduplication. This reduction in the size of the metadata provides an opportunity to use smaller deduplication chunks, does it not? As we know, we get better deduplication the smaller the chunks are, yeah. With the limit being when the metadata starts to get so large that your space savings goes away. Have you experimented or thought about decreasing the average size of the deduplication chunks?
No, we haven't. Because this is not the only metadata overhead. The more important overhead in a lot of systems is the chunk index, and we're actually not reducing the size of the chunk index. For performance purposes, it's an important data structure. But it can be, you can think about that, it's right.
Akshadhar and NEC Labs. For the page-based approach, do you have the extra lookup table that exists that's on SSD? I think that's what you said.
Sorry?
So the lookup table which maps the compressed address that you store to the actual hash, that's on the SSD?
For the chunk-based approach, we actually don't need an additional index, because if you have the code word consists of the page ID and a unique identifier, you can just ask the chunk index itself we already have. You can read the page ID, and you can look up which fingerprints consist to the unique identifier. So you don't need additional index. This is actually a quite nice property of this approach in the system, because you can use the code word as an alternative lookup key for the chunk index in a lot of systems like garbage collecting without additional overhead or additional lookups. So there is no additional reverse index for this approach. The chunk index itself is the reverse index.
Okay, I'll ask you during the poster
okay.
session. I have some more questions.
Hi, Nitin, EMC BRS. I actually have a simple clarification to get from you about your operating model. Are you assuming your data set is frozen, or are you assuming you can rewrite the file recipes periodically?
We are not assuming it's frozen. There are aging effects we are describing in the paper, but what we found out that aging rises slowly. It's not that a full five fingerprint that is very popular at one point in time will be not used in the next week. So you have these aging effects, and there are garbage collecting approaches for the code words, but I have skipped this from the talk.
Yes, but whenever they do change, you will have to rewrite your file recipes.
I'm sorry?
Whenever your code words do change and your prediction models change, you will have to rewrite all your file recipes that are impacted by those code words.
That is a good point. As long as there are file recipes referencing a code word, the code word will be preserved. I mean, I cannot reuse a code word for a different fingerprint as long as there is any file recipe in the system that uses this code word, because otherwise it would point to the different direction.
So exactly, then your code word management will become complicated because your code word is small. It can only encode certain amount of code words.
Yeah, you have to account for that, yeah.
Okay, all right, thanks.